Start recording. Yes. Okay. Hi. Well, no. Um, yeah, Monday again. And this is the last week I give lecture classes in this course. So the content-wise, we are approaching the end. And it was quite diverse content, as you probably experienced. Tomorrow, I will ask you, what's your opinion, on a technical side? I Again, so it is quite diverse in terms of covered topics, but the uniting paradigm is to give you information about various machine learning techniques and aspects besides or beyond the deep learning networks to hopefully you can use this knowledge to solve practical machine learning tasks. The agenda for today and tomorrow is rather simple. So I want to finish the last topic of the last week, which is feed-forward error-correcting neural networks. And in this class, I want to complete the proof of the, well, basically the derivative of cross entropy function with respect to the last two layers of the neural network. And this is related to what you will see in the implementation in lab 5 then. First and foremost, what we have been talking about so far is, let's see, well, it is this architecture. So it's a trace of a single data path from input to the output, passing through several activation, several computing units, which aggregate inputs from aggregate several inputs and compute a so-called activation function. And the whole idea with feed-forward error-correcting neural networks is that, or not the whole, it's like it has several parts in it. The first idea is that given certain input, you want to compute a score of a particular category. So that's first high-level functionality. And this you do by adjusting the influence of this particular of each and every input feature to the computations on different so-called layers. So what is happening inside the layers on a very high level of abstraction is a function approximation, nothing more than that. So at the end, you want the whole neural network, or artificial neural network, is a function is a function of the input and weights. weightings of the particular input features. So all in all, so there is no magic whatsoever. So you fine-tune this universal approximator. That's it. And then you also have, and this you do by tuning the weights as a result of comparing with the ground truth. So with the ground truth, this comparison is done inside a so-called cost function. So there can be different cost functions. You can imagine what it can be Euclidean distance. It can be mean what is it? Mean root mean square error measure, etc. But here is the overall idea. And activation functions are nonlinear functions. Again, the whole idea is to keep the output always bounded. So, which allows for, again, which facilitates the global optimization process. So what we finished last time, we finished at the final step when we constructed, when we decided to choose a specific cost function. So one of possibilities, again, is to not to work with scores, which is produced by the final layer, output layer of the neural network, but rather to normalize them, normalize these values, and treat them as distributions. And in this case, you can use standard measure known from information theory, which is called cross entropy. So in cross entropy, we have two different classes of events. Events of correct predictions and events of incorrect predictions of a particular category. So for a particular category, so the difference between these two probabilities groups are expressed like this. So for a particular class I, so the mismatch between the predictions probabilities and true probabilities. And for all classes then, it is for C and P. It's a sum of the individual mismatches. So this is the cross entropy. So that's what we finished with last time. So now, again, so let us put this last leg of computations together and display it graphically. So we have our hidden layer, last hidden layer. And which actually then collapses into a number of output neurons equals to the number of categories. So here we have number of classes. And again, so the connections are as previously like this. And this output, so this is the output layer. Which produces scores for each category. So what we do now, so these are what we denoted previously as S, small s, 1, S2. So we pass it through this normalizer, which is we defined previously as softmax. And which produces something which we can interpret as probabilities. And so this is our predictors or values of probabilities. And now we pass it to the cross entropy function. So which takes this pi and it takes also ci, so the ground truth. C1, C2, Cm. So, and essentially, or practically, this is a one-hot encoding. So one category is 1, the rest is 0. And so it computes so this H of C and P, which is an error. And it is now that we want to, we almost completed the story, so we want to minimize the error of the predicted distribution versus the ground truth. And we do it, obviously, with respect to, well, so we need to tune these values. So to change these values and see how they affect this error. So this is in the first place. So we want to take a partial derivative of dE by d scores um, and this again, so This can be further broken down by the chain rule to two derivatives. So d no, de oh sorry de by dp. All right. So this will be our first derivative. Multiplied by dpi by d score I. So we need to take a derivative with respect to each score. So this is how it is done. So now I will just sketch a couple of essential steps, and we'll come directly to the final results. So what we do, again, DE for D score I is DE DPI multiplied by DPI D score I. So this first guy over here, DPI. Why am I doing this again? Well, like it or not, I find that I'm using so to basically come from this understanding to the final result. But then again, so I hope that these calculations also will you will remember this non-trivial computations. I mean, from for this last leg, depending on what kind of error or cost function you choose. So if you choose a different cost function, obviously the result will be totally different. So it won't be. You won't arrive to the same simple form as we will now. So d by dpi. So our e, just to remember, so that's sum. Yeah, it's minus sum. Minus sum ci ln pi plus 1 minus ci ln 1 minus pi. So this is the whole thing. So now, taking this derivative of this thing, what do we get? So we get d minus. So now if we spell out this sum over here, so it's C1 ln P1 plus, no, sorry, I will write the whole thing. 1 minus C1 ln logarithm 1 minus P1 minus, And then we have, well, we have all the intermediate steps, CI ln PI plus 1 minus CI ln 1 minus PI. Right? And then you continue this sum further to until the end. But what is important, so now taking this partial derivative with respect to PI, so all the rest becomes 0. So so for all indices which is not I, so derivatives are 0. Therefore, d partial derivative by PI is basically CD. So you take only the I term, CI ln PI minus 1 minus C. Oh. So now we have these two guys over here and these two guys. So basically, the first term is D CI. So CI is a constant. D ln PI dpi minus. Yeah, I shouldn't forget this minuses everywhere. Minus minus the following So this thing is minus CI 1 over PI. So it's already quite good. So here we have a complex thing, which is which converges to this one. So 1 minus CI 1 minus PI multiplied by D one minus PI dPI. Is it correct? Hmm? Hmm? Mm-hmm. Yes. Which on the next step becomes minus CI PI plus 1 minus CI 1 minus PI. Yeah. So please check this in intermediate steps over here.
you put the minus sign on the left, on the last one, not on the right equation. Or did you, wait, is it minus minus? Oh, no.
No, it should be minus minus.
Yes, plus.
Yeah. So that was the first part, so d by dpi. So now we need to take the other one, dpi by d score, and multiply them all. So this one I will just that is the derivative of softmax function with respect to score. So so for dpi d score. So I will just quickly show. So of softmax. So just to remind you, so so this is now softmax of score. This is softmax function. This is score. So remember it had two cases where this score j 1 minus s j. So for so we have two cases for the same the output for the same input. So it's j equals k and minus s j s sk. So when we computed for j not equal k, right? So skipping the intermediate step, so we are computing this function, the derivative, and so that becomes d as s I d s I, which basically goes under this condition over here. So which is, so now this thing is our computed PIs, so the score. So it actually becomes PI 1 minus PI. So this is the derivative. So finally, so when our D score equals to minus CI divided by PI plus 1 minus CI divided by 1 minus PI. So that was the first part multiplied by this thing over here. PI 1 minus PI. So after some simplification, That's already a simple equation. So the final result becomes Pi minus Ci. So which in lab 5 code, so this Pi are y hat, and this one is y over here. So that's what you see there as part of the backprop procedure in the very first computation on the backprop path. So y hat minus y. So it's not. This is not a cost function. It's a derivative of the cross entropy with respect to softmax, so to the result of activation of softmax, and further with respect to particular score. So this part. So all this complicated math so boils down to simple difference between CI and PI, which I think is quite cool. So, and once again, so the main hidden message, if you would implement it from scratch, so instead of that simple formula, so you would first need to properly take, so depending on the configuration of the last layer, so if you have softmax or not, or you have some other function, so you would need to compute this, so you need to compute the proper derivative for the choice of cost function. All right, so let's maybe just to switch the topics, we take a short break now, and then I continue with a different topic. And I will upload the final PDF on Canvas. Bye. So we will talk now about time series processing using, oops. Using machine learning. So, and here I have basically two, here we have two options. First way of dealing with time series concerns feature methods based on feature extraction, and another one is several methods, a family of methods which is feature-based, featureless.
Evgeny, sorry to interrupt, but online we cannot see the slides.
You don't see the slide, okay. Sorry.
No problem.
Let me see if I somehow. Oh, listen, that's even not the correct one I chose. Sorry. The good that let me just pause the recording. Okay. Learning from time series. So as I said, two options we have. So one is based on extracting features, and another one is featureless. But before all, let's agree on a general problem formulation. So we want to learn from sequences, which is variation of a variable in time. So it can be, I mean, in general case, we have a continuous signal, for example. And this is a variable with a continuous domain. Like this can be audio, for example, or any other source of continuous signal. And what first thing we do, or what we can do, we can discretize time and sample the values, so the magnitude of the signal in time. Yes. And what we obtain as a result of this operation, we obtain a discrete signal with finite time resolution. The next step is to discretize even the values, and this process is called quantization. So we define quantization levels, or kind of bins in which we feed the actual values, and we get discretized and quantized signal. So from signal we obtain time series. So a sequence of quantized data measured at discrete intervals of time. And using time series, we can solve several tasks. So one of tasks is classification. So observing the time series, you can decide to which of the categories it belongs to. Anomaly detection, or outlier detection. So that's a typical application, or forecasting. So we can do regression tasks. So to predict what will be the next value at next after the measurement point. So in the future. I personally was involved in a couple of or several projects involving classification of continuous signals, and I want to use this project as examples on how you can approach learning or creating data-driven models for such use cases. So the first one, so let me see which one is. Yeah, basically these three use cases are in the context of intelligent road infrastructure. I will talk more about it. Detection of arrhythmia, so processing of biomedical signals, basically heartbeat measurements, and detecting faults in the industrial context. Another example, which is exemplified on this slide, is the activity detection. So you have measurements of different sensors, and you want to detect whether what kind of activity is performed by a person: running, sitting, laying down, etc. So one probably. Yeah, so one of the use cases we had is detecting the faults in one subpart of a nuclear power plant, where we had many, like 37 measurement points, so different sensors in different key places, and you needed to detect whether collectively the set of measurements correspond to a fault. So a general approach to feature-based method is that so you take your time series and you extract features out of it. So simplest features, what could be a simplest feature? So you monitor for quite some time, and then you collect this first order statistics like mean, max, mean. So this is valid features, but obviously not very precise. As I will demonstrate on other use cases, so designing good features is really well, it's an engineering art, so to say, and because you can design very many features. So first example, so we worked on many years ago, actually. I mean, at that time, I was interested in the current research line. We wanted to have passive monitors of traffic on roads, and so what I mean by passive is that the idea was to attach measurement units directly to the pavement, to the asphalt of the roads. And so these units would be totally autonomous, so that will be battery powered. And I mean, the simplest application would be to count cars. Another application, I mean, more advanced applications would be to detect the type of passing by vehicles. And how you can do that, can do this is by measuring changes in magnetic field. So we had a magnetometer installed on the processing unit and vibration in the pavement. And apparently with these two signals, you can decide on the type of the measurement, so on the type of vehicle passing by. Yeah, and so looking or talking retrospectively, I mean, this technology wasn't installed. I don't know if it was installed in other countries or not, but I mean, one of the major challenges is the durability of these devices. So we experimented with different materials, but I mean, especially here in North, I mean, we have very tough conditions, especially during winter with the plowing machines. So they were simply scratched from the surface. I mean, but again, so when you approach a machine learning task, first thing is to look for data and how to, I mean, what to classify. So there are some well-defined categories on classification level of vehicles. So examples are here. I mean, I will not go into too much details of it, except for that there are 4 different classes. So we have light vehicles, and then we have heavy motor vehicles. So basically different in number of axles and such like that. And what we did, first we ran quite some experiments and collected data. So we had test environment close to Alvik. So there is a bridge over there just after the speed meter metering camera. So we installed this device, but it was connected to a computer, and we carefully recorded all the passing vehicles and manually classified them. So and that's how a typical signal when a vehicle was passing by such a unit look like. So magnetometer on the right, accelerometer, magnetometer on the left, and accelerometer on the right. Looking a little bit ahead, so what you can see here visually, at least. So there is some pattern, and this pattern actually, well, first of all, what is it? So here it is, you see some pattern that corresponds to passage of axles. So they here and here. So, and the feature extraction method, it worked like that. So we defined 5 features. So feature 1 is it's called discrete time integral of the magnetometer magnitude. So basically we sum up magnetometer magnitude according to this formula. So that becomes feature 1. So for the whole signal. Then the same goes for z-axis of the accelerometer. So this feature 2. And then this 3 other features were defined by first extracting the areas or portions of a signal with drastic changes. So that's kind of very classical signal processing technique. So you monitor the lower level, then it suddenly signal start to increase. You mark it as the beginning of the window. Then so when it returns back to the floor level, to the noise level, floor level. So you end the current period, so you monitor again, so signal start to increase. So and in this way you define the areas of interest of a signal. So this was the feature extraction process. Again, so that has little to do with machine learning. So the techniques are classical signal processing techniques. But then when you extract the features, so to find the pattern in them, we used various machine learning techniques, including well, you don't need a very deep neural network here, but regression amongst others we used and other stuff. So the next and of course, okay, let me comment on this at a later point. So the next use case, so we had a project sponsored by Swedish Research Council, so together with Umeå University Hospital, University Hospital. So we had a medical engineer there. A researcher specializing in processing of heartbeat signals. So and the idea is that so you measure the heart signal, and this is the classical or form of a heartbeat. So PQRST module, and so which corresponds to a single cycle of a heartbeat. So you can, I mean, if you ask this person, so he will explain what happens with different parts of the heart during each of these signal periods. And the idea is basically, and different diseases or people with different diseases, they exhibit different distortions in this in this PQRST pattern. So I mean, some parts can be less less smoothed out or not existent at all, and depending on this distortion. So normally people suffer from different heart diseases, different types of arrhythmia. Yes, and uh, and again, so the steps before actually inputting anything to machine learning methods, so one need to do quite a lot of classical signal processing, like noise filtering, extraction of this PQRST sequences, etc. Or QRS complex, it is called. So all these techniques again are known. So and part of MATLAB toolbox, or you can find similar libraries for Python, I guess. And then one interesting. Oh, sorry. Let me see if then this one is still valid. Yeah. So some summary. If you're interested, you can read it here. But the point for me to show in this, probably to still see my screen in Zoom, because normally when I do it, it disappears.
Yes, we can see it.
Okay, good. So you can define lots of features in the, I mean, depending on how you look at the signal. So you basically can define features in time domain, frequency domain, morphological features, etc., etc. Let me see if I have it. Yeah. So what I mean by this is that when you approach solving a problem with in a specific domain, and for example, you are not working with standard databases with already extracted features. In many cases, the essential part is to have a domain expert who knows how to actually deal with the specific signals. So so each domain they have very different challenges. So we started with so we as part of this project, so we looked at one of the challenges. So they have every year, so each or many applications domains, so they conduct their own challenges. So if on achieving best classification of one or another disease or whatever use case you consider. So at that time we were looking at a cardiology challenge. Challenge of detecting types of arrhythmia, and the winning team, so the one that produced best results. So they trained their classifier on 171 on total 171 features. So again, so coming back to so these features, the list of these features can be found here. So 171. So you need to you can extract. Then what we did, we actually then again the question is, do you need all these features for good enough detection? So you always have to balance the maximum possible accuracy with accuracy which is sufficient for your specific use case. So especially, and here our question was, what would be the maximum possible accuracy if you would think of creating the minimalistic model, so suitable for detection on wearable devices. And so we apply this technique. Well, it's a kind of part of training methodology, which is recursive feature elimination. And finally, out of 171, we derived those 15 that actually the combination of which produced the best result. And then when you do that, so then you already within this course, we talked about different techniques what you can do with it. Do you have a labeled data? You can train a classifier, or if you want to visualize, well, you have plenty of visualizers at your disposal. So here, for example, we tried it on our some self-organized maps implementation and see how they. So different types of arrhythmia is arranged with respect to well, specifically atrial what is it? Arterial fibrillation, atrial fibrillation. Yeah. I think I want to stop at this point. So tomorrow we will talk about feature-less methods. And overall, I want you to maybe collect some reflections on the technical part of the course, so that I can answer your questions basically. So that's it for today.
Yeah, can I ask a quick question?
Yeah, absolutely. Go on.
Yeah, it's about the seminars. I
Mhm.
don't know if you